Hello viewers, welcome to my channel Physics with Rams. So today we are going to discuss about transverse modes of vibration of a string. So when we consider a rigid support, other end of the string is being attached to a block of mass so that we can generate the tension across the string, and when a wave is being passed across the string, it returns back forming a stationary wave. Observe that a node has been formed at this endpoint, and in between we have an antinode as well as a node is formed at this location. Remember that a node is nothing but its vertical displacement is minimum, whereas antinode is nothing but its vertical displacement is maximum. So based on antinodes and nodes, a wave will move in the forward direction. Suppose if we consider a free end, instead of forming a two nodes and antinode, a single node as well as a antinode will be formed across the string when it is being attached to free end. And since it is a rigid end, here we get two and as well as two nodes and one antinode. So it's possible when we plug at the center. Here when we consider the displacement of the first wave, as I consider it as a first wave, the displacement of this wave is being given as y equal to a sine omega t minus kx, whereas the displacement of this second wave is being represented as y2 equal to a sine omega t plus kx. And according to principle of superposition, we know that y equal to y1 plus y2, and substituting the values of these two expressions, and when we simplify it, here we get 2a cos omega t into sine kx. So this represents the resultant displacement equation, and by using this equation, now we are going to represent the condition for transverse waves. When string is fixed at both ends. So I'm going to consider a string such that the number of loops are being formed string. Number of loops are being formed across the string. So here I'm going to consider that the p loops has been formed across the string, whereas we know that the wavelength of half of the wave is being represented as lambda by 2. So when we consider the complete length of the string, we can represent that p into lambda by 2 is equal to L. So by using this equation here, we can represent lambda equal to 2L by p. So this represents the wavelength p loops. Whereas when we consider a string, the speed of the wave across the string is being represented as T by mu, where T is tension as well as mu is linear density. As well as we can represent mu equal to m by L, mass per unit length. When we substitute this two values, this value speed and wavelength in the expression v equal to f into lambda. We can represent f equal to v by lambda. So let's substitute the values. So that p by 2l into under root of t by mu. This represents the expression for frequency, and it is a common equation. Based on this common equation itself, we can represent the number of modes formed across the waves. Okay, take a screenshot. We will continue. So as you observe that if a single loop, is formed across the string, then we substitute p equal to 1, whereas the frequency f1 is equal to, in the place of p we substitute 1 by 2l into under root of t by mu. So we call it as a first harmonic, or we also represent it as a fundamental frequency. Whereas if we consider two loops has been formed across the string, we can substitute p equal to 2. So the frequency has been given as 2 by 2l into under root of t by mu, where we represent it as a second harmonic, or we represent it as a first overtone. Whereas when we consider three loops has been formed across the string, so we can represent p equal to 3. Then the frequency is being represented as f3 equal to 3 by 2l into under root of t by mu. So we represent it as a third harmonic, or we represent it as a second overtone. In this way we can represent the harmonics as well as overtones based on the number of loops formed across the string. Take a screenshot. We'll continue. Okay, as you consider this, the stationary waves across the string are being represented with a sonometer. A sonometer consists of a wooden box on which two bridges will be there, and one end of the string is being tied to a fixed end, other end is being suspended over a pulley, so that a block of mass m is being attached in order to create tension across the string. So as you consider this diagram, sonometer, when we place it in the air, here observe that the tension is being represented in terms of weight, T equal to mg. Suppose if I dip this in a liquid, the tension across the string is being represented as T equal to mg into 1 minus density of the liquid by density of the body. Density of the liquid by density of the body. Then based on this we can represent the frequency, as we know that frequency P by 2L into under root of T by mu. So when we substitute this, here we have P by 2L into under root of mg into 1 minus density of the liquid by density of the body by mu. So this represents the expression for frequency. Similarly, when we consider the Young's modulus of this string, we know that Young's modulus equal to FL by AE, where force is being represented based on the tension, so we can represent a TL by AE. So when I consider this, T equal to YAE by L. So this represents the tension based on the Young's modulus. Then the frequency of the wave formed on the string is being represented as P by 2L under root of T by mu, right? So T equal to YAE by L into mu. So this represents the frequency by representing based on Young's modulus. Take a screenshot. We will continue. Okay, now we are going to represent the effect of temperature. Effect of temperature on a vibrating string. Vibrating string. So when we consider this, observe that the frequency is being represented as P by 2L into under root of T by mu. T by mu. When we bring this L inside here, we can represent P by 2 into under root of T by L square into M by L. One L gets cancelled, so here we can represent P by T into under root of T by M into L. So this represents the expression for frequency in terms of number of loops, tension and mass and length. So here we can represent that frequency is directly proportional of T by ml. So when we consider the change in frequency with respect to actual frequency, here we can represent that frequency is inversely proportional to length. Why? Because as the temperature changes, the length of the string changes. So here we can represent the change in the frequency with respect to actual frequency is being represented as 1 by 2, since it is in denominator, minus 1 by 2 into delta L by L. As we know that the coefficient of linear expansion is being represented as delta L by L into delta T. So from this equation here we can represent the delta L by L is equal to alpha into delta T. So when we substitute here we can send 1 by 2 into alpha into delta T. So this represents the expression for change in frequency, based on change in temperature, change in the temperature. So take a screenshot, we'll continue. Now we are going to represent the laws of transverse waves. So come to the case of this. Here, as you consider the formula, we know that F is equal to P by 2L into under root of T by mu. So when we consider that a tension and a linear density are constants, so we can represent that frequency is inversely proportional to length. So based on that we can represent F1 by F2 is equal to L2 by L1. So this represents a first law, whereas when we consider this second law, here we are going to represent L and mu are constant, means length and linear density are constant, whereas we are going to change the tension. So based on that we can represent that frequency is directly proportional to square root of tension. So here we can represent F1 by F2 equal to under root of T1 by T2. So this represents a second law. Whereas in the case of third law, we consider L and T are constant, length and tension are constant. Then here we can represent that frequency is inversely proportional to square root of linear density. Then we can represent F1 by F2 equal to under root of mu2 by mu1. Third law. In this way we can represent the three laws by considering the expression of a frequency. Take a screenshot, we'll continue. Okay, now we are going to solve some problems based on these concepts. Observe that first question. A guitar string is 90 centimeter long and has a fundamental frequency of 124 hertz. Where should it be pressed? To produce a fundamental frequency of 186 hertz. So already we had seen that we, based on the length, we have to represent the frequency. As we had seen the first law, frequency is inversely proportional to length. Then we can 1 by f2 is equal to L2 by L1. Let's substitute the values so that we can find out L2 equal to f1 by f2 into L1. So 124 by 186 into length of the string is 90 centimeters. So here we get 60 centimeters. So this represents the length at which we have to plug so that it vibrates with a fundamental frequency of 186 hertz. Take a screenshot. We'll continue. Observe the next question. A wire of length 1 meter and mass 20 gram is stretched with a force of 800 Newton. Find the fundamental frequency. Also find the frequencies of first two orbitals. So the formula for frequency, fundamental frequency, is represented as f equal to 1 by 2L into under root of T bar mu. As you had observed that the length has been given as 1 meter and its mass is 20 grams, as well as tension is being given as 800 Newton. When we convert this mass 20 grams into kg, here we know that m is equal to 20 into 10 to the power of minus 3. So we can represent 0.02 kg. As we substitute the values, 1 by 2 into 1 under root of 800 by 2 into 10 to the power of minus 3. So we have 400. So we get 1 by 2 into under root of 4 into 10 to the power of 4. So we can represent 1 by 2 into 2 into 10 square. 2 into gets cancelled. So here the fundamental frequency is 100 hertz. So the first overtone will be 2 into 100, nothing but 200 hertz. or else the second overtone is being represented as a 3 into 100, nothing but 300 hertz. Take a screenshot. So before going to end this video, my request is please subscribe my channel so that you can watch my videos regularly. Thank you.